So welcome everybody. Thanks very much for attending today's webinar session. For those that don't know me, my name's Blair Smith. I am Innovation Lead at Melbourne Water, and I'm also the Deputy Program Manager for the Knowledge and Collaboration Program at the IWN. So today we have the next chapter in our webinar series. And so for those that aren't familiar, these webinars are made available on the Knowledge Hub through the IWN. So if you're looking for a bit of a recap after today's session, or if there's somebody, perhaps a colleague that you'd like to share this with, you'll have the ability to share this through the IWN portal after today. So we've got a really interesting and quite a unique solution regarding water quality monitoring today. And the idea of this is to bring together machine learning and really extensive data sets for quite a unique take on water quality monitoring. And so in a second, we're going to hear from Dr. Vishy Karri, who's the CEO and founder of Expert365. Now, Expert365 and indeed Dr. Karri have won numerous awards and accolades for both the small business and as a very successful startup and on a more personal level from innovation, and particularly in engineering. And we're going to hear really about the solution that Expert365 have developed. We're going to get a bit of a demonstration of that, talk about how it can benefit our particular industry, and what a trial might look like for the water industry as well. And so if there's interest from the members today to explore this particular solution, then we as the IWN can obviously support you in that. We can facilitate a trial. So certainly that's one of the outcomes that we would look for today, is to see if there's some particular interest in that area. So just in terms of the formalities for today, we've got a presentation. We've left plenty of time for questions at the end. So if you do have questions or comments, you're welcome to write those into the chat section, or alternatively hold those towards the end, and we'll address those as part of today's webinar and presentation. So that's it from me. Thanks again for attending. I'm going to hand over to Dr. Vishy Karri to present on Expert365.
Thanks, Blair, and thanks, Dean, for organizing this. Firstly, it's an honor to sort of see such a large collection of people in water industry interested in this technology. Before I sort of get into it, I just give you a little bit of a background on how it all evolved. I think it's quite important. So you will actually see how it was built systematically and not over a weekend or over a season. One season. It all goes back to 5 years ago, literally 5 years ago, when we were doing some basic tests in understanding water. So, okay, we built IoT solutions initially and build some sensor suites that are able to send signals like pH, EC, TDS, DO, ORP, those standard stuff. We are able to put them remotely, and we are able to measure a handful of data, sets of data initially. So we don't have to run around with our four-wheel drives to these remote areas and start putting those things physically to measure it. So that was the original intent 5 years ago. And when we started getting the data, that's when things starting to get excited, because we had a group of, I come from a strong AI background. Those who have probably are not aware of my background, I'm a professor in AI, ML engineering, applied engineering, and I have been a professor of engineering. I hung my boots with universities and started this. There's a very sound AI, ML baggage that I had to somehow apply it to get it off my shoulders. So we looked at this data coming in, the standard physical measurements that are coming that most of you water utility companies are measuring on a daily basis. And so what do we do with it? What else can we do with it? So with a handful of physical parameters that we are able to measure, which is pH, EC, DO, turbidity, ORP, the standard ones, what I call the suite Sonde standard suites or Sonde measurements. Can we do something more exciting with it? And that was the start of Expert365 journey. So we went ahead and then said, okay, can we understand a little bit about the bacterial activity inside water, given the weather parameters, the other water physical chemical conditions inside the water, including ability to measure carbon dioxide, the nitrate levels, ammonium levels, and all that. Say, can we do that? And suddenly there was a patent that we could manage to secure a patent. I said, okay, look, I think we can do a reasonable accuracy, E. coli or fecal coliforms and total coliforms that we are able to do it. And what we are doing with AI is actually matching laboratory results, give or take 10%, or that seems okay, but that was for one season. So we said, okay, this seems to work, but let's just go and then build it a little bit more and see if can I do a COD perhaps. Can we do biological oxygen, BOD, and are we able to give a little bit on the color perhaps? So it's starting to expand. And that's how what you will see today, in the presentation today, has grown organically and now tested over 14 seasons. So the knowledge base, the knowledge bank, that AI ML knowledge bank, that is what you will see over 14 seasons, 3.5 years, live testing data with 2.5 million rows of data points validated inside the laboratory. So when the AI is spitting out the data, the laboratory test, we confirm and say, look, you are 20% out, go improve your model again. And that has helped us to build a digitization model that is very unique, which I'll also share now. So without much ado, I'd just like to go with this presentation. The way I'd like to structure this is I would like to say, look, I'll give you the concept layout. What does the AI ML predictive model looks like? You all have sensors available. You are not into, for example, if an innovation group comes from your organization and says, look, I have this fantastic technology we can adopt, but the sensors outside will cost us $10,000 to put in. The first thing is you have 70 or 80 monitoring sites, and then you have $10,000 per site of installation. You say, look, I'm not interested in that anymore. The pressure on the sensory equipment purchases has shut down many organizations from even innovating. They said, I can't be bothered, it's too expensive. I don't know what's the next stage of sensory input coming in. I have established SCADA systems. I have fantastic systems that I have incorporated with a handful of them, half a dozen, sometimes 3 or 4. I'm getting my reliable data every day. What can we do with that data rather than sell me another $10,000?
Sorry, Vishy, you've seemed to have jumped on mute. I can't.
Can you hear me?
I can now. Yes.
But did you hear me so far, though?
We probably lost just about the last 20 seconds of your commentary.
Yes. What I was saying is that the real-time sensor solution, the concept and all that, followed by the digitization model, is what I would be talking. And then what we are doing in the third world countries. Okay, we got this beautiful Australian innovation patents. We collected a handful of those. Now we're going to Bangladesh or Sri Lanka or India or somewhere where the distributed water network is stored on the overhead tankers prior to distribution into these villages. So how is that system? How did we employ those? That journey And then a little bit on Water 365 solution, which I think is the most comprehensive solution. It's not quite, we are testing it. The validations are going on every day. But Tank 365 solution, which is the solution approved by they call the Ministries of Water and Environment in few countries. It takes 14 parameters approved by the World Health Organization for portability and shows them online. I'll give you those examples. And how AI ML, where does these solutions as an innovative tools coming out into the market, where do they stand compared to what is their value proposition? Where do they fit in terms of the market? I'll very quickly show some live examples of it. So now if I could take to the next slide. Right. Allow me to share this quickly. If you look at this real-time sensor data, you can have that, or you could have a historical data. So some organizations may say, look, I want to try it purely on my historical data. I have very sound data available. Show me if these models work. I don't want to put any instrumentation for now. OK, so you have the historical data, and you also have the ability to do through the real-time sensors. Now, handful of sensors, DO, EC, ORP, temperatures, turbidity, we are measuring them every day, some of you. And that goes, along with the weather data, goes into these engines. And then these are the virtual sensors that are coming out, hard to measure. Well, if I take, it's not that we can't get BOD, COD, but BOD 5 takes 5 days. And COD is a little bit more tricky in order to get it accurately. Color is even more trickier, although the methods are fairly straightforward and well documented, still tricky. And residual chlorine, I mean, you're putting chlorine prior to the distribution. And by the time the chlorine goes from Heidelberg to Q, the water distribution goes through. How is the residual chlorine actually varying in those suburbs? Because even you're always thinking, I have added residual chlorine. I know that the percentage, the amount of chlorine, residual chlorine I need in the water has to be so much for compliance. But we have put it in, and let's hope that it's going to work. So we need a finger on the pulse on that, using some smart systems to be able to detect. So we do that. They spit it out, and they are measured with lab. So they go, say, OK, you are saying your residual chlorine is 0.8 ppt today. Show me that in the lab, what does it say? The lab says 1.2, 1.1, you are out. They'll go and then fix your model. So it goes, and then this machine adjusts that and comes up with saying, I know how it works now. So that's the way the cyclic process is working. This is the digitization model. Allow me to spend a few minutes on this. The water digitization model is, these are all, firstly, we develop based on the IoT sensory inputs, we develop the data collection. Okay, we are getting this pH, the EC, the TDS, the DOs, we are getting them. Once we get them, we have some preliminary models that we are checking. And to see if actually what we are measuring and what we are predicting makes sense, I need a handful of data for laboratory testing. So I go and do that. Then we sort of look at it at some point. I am measuring so many weather parameters and handful of physical parameters coming from the physical sensors. Do all of them I need in order to predict these complicated COD, BODs, or can I cut them a little bit? So that's where the feature engineering comes into picture. And then say, look, I identify those significant parameters that are contributing to the predictive capability of those hard to measure parameters. So some of those fall off at the end of the truck. So we have those parameters that are now good to go for predictability. And that could change every time, because some of those, depending on the season, some parameters get more prominent than the others. So we come back to the stage number 4, and then I have a structured data where I'm able to build a predictive model. And we say, I do a periodic revision of those machine learning models. Because if the laboratory is the authority, if the lab is saying I'm 10, 15% out, I better go and then fix the ML model, and it's done. So the periodic revisions keep going. And then suddenly on the stage 6, we have an improved AI ML model that is ready for the deployment online. And that's when we have an arduous task of putting them online. Most of these AI ML models that you probably are aware, they all talk about offline testing. They say, I have predicted this, I got 90% accuracy on the predictability of my parameters. That's fine, but I want it online. Can you put it online for me? I want the data is coming, sensors are all coming online. It has to give me decision online. I should be able to see it online, and I have to have a bird's eye view of every installation or every testing site online. So which means these, on the stage number 7, we have a challenge to deploy it online where the online data is coming, and then we are able to show it on a web-based interface. I'll show that to you in a minute. And then, of course, there is the learning never stops. Just for the, just like us, the machine learning, it just keeps learning. I'm better than what I was last season. I'm better than what I was 6 months ago. I'm certainly better over 2 seasons, 2 consecutive years, and I'm definitely better in 3.5 years, because it is seeing the data evolve. You all know that just when we think we have identified a means to predict, for example, nitrate levels in water dams. For example, I'm giving you an example. Okay, we all look at that and say, I have 1 year of data, and I can reliably now estimate what is the nitrate levels in month of June very accurately. But it just so happens that that particular month of June is an aberration, and we had some rough weather and the nitrate levels shot through the roof. And that 1 year of data is suddenly inadequate because it doesn't best represent the nitrate behavior over a year, over the season changes. Right? So this is what the ongoing algorithm improvement on the stage 8 as a part of the digitization cycle is ensuring that we are learning with every season, every year. The data now, the challenge, of course, the vision is that these results match very, very close to our laboratory results. But at the moment, if you look at a situational awareness, we really don't have 100% situational awareness until we go to the laboratory with a bucket of water. Now, this is, allow me to share very quickly this Tank 365. These are all live sites based out of the subcontinent. And the way we do that is we have, as a side technology, we also have a UV as a secondary disinfection to existing chlorination processes. And then the water is distributed from these overhead tanks into these villages. And they eat typically 20,000, 50,000 people in a village. And some of them could have a tank close to 500,000 liters or 1 million liters, and where it is servicing populations up to 250,000 people. But this technology, the way it is going is, as soon as the water starting to get distributed, it starts to measure the water quality based on handful of physical sensors, and it is able to sort of give us what is E. coli, fecal coliforms, fluoride, residual chlorine, coliforms, total good or bad altogether. And then, of course, the physical measurements from the water. So this is able to give a handful of these parameters live. So the government is able to sit down and say, I have currently 20 villages, that's what it's working on. And I have a bird's eye view of the distributed water quality from these overhead tanks, post disinfection using UV, the quality of water to end mile user. That's what they are trying to do with this technology. And I mean, we use that sensor. What you're seeing there is one of the sensors as a video, where that's one of our sensors, but that's not, you don't need to have that, as I mentioned to you earlier. Your data can feed in. So now the next part is the Water 365. This is a lot more comprehensive. So we are actually starting to say, I would like to have a suite of metals inside the water. I would like to know from aluminium, arsenic, cadmium, and so on. And then health and aesthetic parameters, give me BOD5, carbon dioxide, dissolved oxygen E. coli, ORP, and so on. We are able to do that, and then I'll get to that in a live demonstration. So now allow me to quickly refer to the Engineers Australia as early as January this year in Queensland. They have put this is a part of their recommendations to water industry that they have put in. I'm pretty sure if some of you are from Queensland, you will understand what I'm saying here. They are focusing on, if you look at the outcome benefits number 2, use of advanced data analytics, AI, machine learning, and visualization to produce real-time insights. We are still working on it. Many of the water industry is working on it. And data collection and sensory systems. Now, the risk, it is also saying that the spatial data portals provide limited access to key information. And also many other types of data and reports are unavailable. And then there is also only data that is shared is what is complied. Because people are so scared of even a non-persisting non-compliance is a big taboo in industry. While a non-persisting non-compliance is the nature of water. It is possible that I have the ammonium levels shoot through the roof over 6 hours of time and settle down again in a dynamic nature of water. But when that happens, which we can see on in our examples, I'll show it to you. But what we tend to do is send it to the laboratory, do 20 times testing, make sure it comes out as all good stuff, and then let us just give it to the regulator. We are saying, yeah, we are fine. No worries about that. But the understanding, having to accept a non-persisting non-compliance is nature of water is still not. I know a lot of colleagues out there in water industry, but it's still not quite a concept that they can embrace. They say, hey, let's not talk about non-compliance at all. But coming back to this technology would help to systematically, meticulously document the data over periods of time. So we see a non-persisting non-compliance, even if it is for a short time, we understand the science behind it. So that's one aspect of it. Now, why these AI ML technologies are unique and why this is very important slide. What I'd like to see is that each time the data is going to the cloud, it is comparing with the World Health Organization standard limits. So if the value is coming to be well within the limit, it spits out a green. If the value is on the border, it puts a yellow. And then if it is non-compliant, it puts red. And again, AI ML have the ability to forecast, to predict these hard to measure online bacteria, for example. And that is an added bonus with these technologies. And also, as I mentioned earlier, ability to do over 4 seasons. So it is building on a sound knowledge of seasonal changes rather than an ad hoc overnight weekend testing. So these are the applications. Like so, we can apply to virtual sensors. We apply to forecasting water quality, and then checking portability, desalination, and also the transient know-how of what the water portability is. Now, if you allow me to very quickly show the AI ML, if you see the y-axis is the rapid situational awareness. So if you have a low situational awareness and a high situational awareness, and then as a part of the suite. So this is low on the left-hand side and very high ability to measure large number of parameters on the right-hand side. So if you see that, we know interactive coupled plasma spectroscopy is somewhere there, and combined offline multi-probes are all out there, and SCADA instruments, handful of data, but you have situational awareness, reasonable. But if you look at this AI ML, very high situational awareness and a very high number of parameters, and often awareness of the situation. What is it likely to be? I'm sure many of you would have gone through the situation where, say, I have to wait for a week before I get the lab results out. What you reckon would be the manganese content in there? Can somebody give me a rough idea what it should be like? What could be the values in there? Plus or minus 15%, 20%? Give me some awareness. I'm sure we all would have gone through that scenario at some point. Now, this is an example of we've done it in Spain, where you have these sensors data coming in using combination of historical and sensory data. We predict the dissolved oxygen, the nitrates, the ammonium, and of course the phosphates as a sequence. Now, before I sort of give you the examples of it, I request you to kindly, if you could kindly download an app on the internet, please, if possible. It is available on the app stores as any app, Google, Android or iPhone. Please download Tank 365 and use these user credentials, please, so that I can actually take you now straight into I'll show you how the system works. So if you could kindly make a note of that, it's Alicante E365. And now I will take you to the live demonstration.
Those details are in the chat also for anybody who wasn't able to capture that quickly.
I'm sorry, say it again.
So we've pasted those details into the chat as well. So if anybody is still working through that, you'll find that data in the chat.
Wonderful. This is great. So now if I could again sort of share I will share now I will go now. I'll share this now. I'm actually taking you straight into, if you are able to open that login details, please. So you'll actually see what I'm getting at. What you are looking at, Alicante, it's a as you know, it's a region in Spain, and we are doing some work looking at the water distribution, and also it's live. What you'll see is actually it's a live data. So allow me to go there straight. So it's aqua. So it's Alicante. So this is so what you're seeing here is so we are looking at is El Campello, and then San Jose de Alicante, and these are few Urbanova Alicante. We have these few areas picked, and say, okay, give me the physical and chemical parameters for El Campello now. So that's the thing. It's 11 degrees centigrade there, a bit cold. pH is 8.17, EC 0.76, which is 760 if you talk about microsiemens per centimeter. And salinity, alkalinity, residual alkalinity, hardness of water. As you know, this is fairly, you know, the Spanish water is it's not very soft. And then you could also say that, look, give me the health and aesthetic parameters in Monte del Sol, that's now. And then suspended solids is so much. ORP is 272 millivolts. Its total coliforms is 3,000. Good and bad. It's pretty good. The color is 5.1 PCU and turbidity is 0.19. E. coli is 0. There's no hazard. And the BOD, CODs are 0 in the distributed network, and then dissolved oxygen of 7.6. So you could see that the live snapshots we are getting these. And you could also come back and then say, show me if this water, for example, many of you where you are administering dams, the water is going to agricultural farmlands. Some of them, not all of them, some of them. So what would that water, if it is going through an agricultural farmland, have an impact on? What would be the phosphates levels in there? Sodium absorption ratios is so high. It's like it'll make it's pretty high. The SR ratio there, and then the mole ratios, and then the total nitrogens there, figure of merit. These are all what is the most likely values there before we run to the lab and find out. But we have the awareness. And this is the price of it. If you see that, this is where you can actually say that, look, show me the levels of, so this is a suite of metals: aluminum, copper, titanium, zinc, mercury, chromium. This seems like reasonable good water. And if it is yellow, it is on the border. And then its silicon is like 85 milligrams. And so on. So this is giving an awareness of water thumbprint at that particular point. So if you allow me to go out of this, and I will now take you to river. I'll take a different time. So we are talking about you also are administering the estuaries, the little rivulets going through. How do they look like? And then this is, firstly, before I explain this, I have to thank the Murray Water Basin for providing the data to be able to model these things. And this sort of give me the physical and chemical. These are the 14 parameters that, again, the World Health Organization has identified as potability. And it is giving the pH and 16.5 degrees, TDS, total suspended solids, the turbidity so much, dissolved oxygen, and ORP, getting those values. And we could also say that give me the health and aesthetic for Rochester. And yeah, it is it's giving those values like iron, aluminum, arsenic, and so on. So what I would now like to show you is a scenario where you actually have an overview. For example, if you want to go and then say, I have my 20 sites that I'm monitoring, and please give me, for those small reservoirs that I'm monitoring, please give me a bird's eye view of all these measuring sites that we are doing. So every 30 seconds, it just keeps moving. So you have a bird's eye view of all these locations. And also, another thing that we could also do is that we could go and then say, look, give me historical data. Give me the historical data and show me for river, and I want it from let's go. This is what it is saying. I'll just historical view report. And then I just say site is, and show it to me for today. Was this for today? And so we got 3 readings today, and then the temperature, TDS, ORP, so on. So this is the sort of detail. So you could have it for years. You could be doing it for years. Some of the parameters you can have it for 10 years, and then where we are able to measure or record that non-compliance that we were really worried about, sort of reporting, but to have a good understanding what physical chemical parameters contribute to that non-persisting non-compliance is also a body of knowledge that is stored in there. So I think I'll stop here. I think I have shown what it can do, but you can actually see on the Alicante in your mobile phones, when you actually downloaded it, you actually could see what are the physical chemical parameters on the mobile phone as well, which is a live data. So I will actually stop there. Blair has given me 40 minutes, and I'm just about there. And I thought I will stop there and then encourage a discussion and maybe answer some questions if you have some questions.
Fabulous. Thank you very much. So yes, I mean, happy to open for questions at this point in time. I'm not seeing anything in the chat, but feel free to jump in with any particular questions that you may have. But I will kick off with a particular question. And the question is, so I understand that what the solution is doing is ultimately predicting values, and it's using a combination of historical data and obviously the algorithm and weather and the likes to determine that, in addition to SCADA sensor data that we would have for a various location. If we have a location which has a very bare minimum number of sensors, is there a particular, is there a minimum number of sensors that you have to have in a particular location for this to work?
That's a really good question. Thanks, Blair. Although it is asking for those 6 parameters, the minimum number we need, and like, for example, it can, of course, the accuracy gets slightly compromised if you don't have those additional parameters, but it is smart enough to estimate. I'll give you an example. PHEC, the ORP, and turbidity. These 4 are adequate, along with the weather parameters, to give you those suite of parameters we talked about. If that is the minimum most you can go to, below which we can't do it. Okay? So answering your question, minimum physical sensors are 4, and then, of course, if you can have the other like the dissolved oxygen and if you have additional dissolved oxygen sensor, that will help, particularly for the health and aesthetic modeling.
Thank you. And we have a question in the chat, which is how can it work in a Class A recycled water, and have you tried in wastewater as well?
Have you tried in wastewater as well? That answer is I have not tried it in wastewater. This is all done in potability and fresh water, and we also tried it in freshwater aquaculture, which I think that too non-brackish freshwater aquaculture. So we have so coming back to that Hiral's question, not there yet, but we'll get there. I also see that do you just supply IoT software platform or required sensors? The answer is we do have a suite of sensors. We supply the suite of sensors as well, but we would like to tap into your existing SCADA sensors because the system is available to be able to just take it and run with it. But we do have our own dedicated OEM sensors. We do it with HANA instruments, and that can be provided as well. So that's where I see that Paresh Modi's question that. And the Kevin Heller saying, does the visualization show confidence in so well? The confidence interval is post After testing the laboratory, the model is getting updated. That's a very good question, what Kevin just raised. Does the prediction gives any range, he's asking. So is it a 95% confidence level or 99% confidence level that you are okay with it? But the answer to that is, it is currently, for the 14 seasons tested, it is plus or minus 15% accuracy on the hard to measure parameters. And for relatively easy parameters that are weather dependent, it's plus or minus 10%. So it's reasonably close for provision of the awareness.
Feel free to jump in with any questions, folks.
Yeah, absolutely, yeah.
Another question from me is, you were demonstrating when you were showing us the history, you were sort of showing intraday readings. So is that a case of the algorithm recalculating multiple times a day, or is that sort of more of a reflection of updated sensor data, so SCADA data coming into the system?
Perfect. The model gets updated once every month, but the data is live. The live data is coming, and even sometimes quicker than a month. We look at it that, for example, when we were doing some tests with manganese estimations using this technology, we were out by miles. We just couldn't understand. We said, how come we are out by 20% on these estimations? And it just so happens that if the transmission data is wrong, okay, let me explain this. When the SCADA input, for example, we know in a very rough scenario, we know that a pH should be between 4 and 14 and not an 18.5, because the SCADA system is faulty. So the system starts to go berserk. But those things are also taken into consideration. But coming back to your question, it gets updated depending on the complexity more than once a month. And the data is changing regularly every minute, 2 hours, 1 hour. We can set the frequency of what is the frequency of transmission, and the data is changing because the two numbers are never the same in a dynamic situation.
Right. So if I'm understanding that correctly, what you're suggesting is the training, as in how the algorithm is going to perform, is updated averagely on a monthly basis, but the actual information is in the readings as to what they would be. Could be as frequently as hourly. So you're getting very current information.
5 minutes, every 5 minutes. Technically,
right.
we can. Yeah, and I also see one more question, that how many years of data at first is required for the engines to start giving predictions? The current data is ready for prediction. I'm requesting you, those are all online. I request you through Blair, you can actually send me an email, say, I give you this set of parameters. For my organization, I want you to give me the predictions of all these parameters for a fortnight. Try that out. Please send that to me. And then let our team actually give. So you will build a bit more confidence into how these tools work with your historical data as well as your limited SCADA inputs. So we could try that. I'm happy to run those trials for you, as Blair said in the beginning of the conversation.
So just digging into that a little bit further, in terms of a trial, so if a water authority is interested in exploring this particular product, my understanding is that we could simply provide you with some recent lab results. Would that be adequate?
That is just adequate, just to get so that you could actually see, and then when the results are coming out, my only request is that if you are able to kindly give me a feedback on what your laboratory results are saying to what the AI is predicting, so we actually can get it so close to your laboratory results in a matter of week or two for your organization.
Right. So I think what you're suggesting there is, so we would initially provide some lab results, and would that be perhaps 6 months worth of lab results?
Just a fortnight is good enough. Fortnight.
Okay. And then obviously as the system, that's sufficient for the system to be making predictions. And then what we can then do is, as new lab results come in, we feed that back into the process, and the virtual sensors become more accurate as the system learns.
Correct. And that means that technology, those algorithms are your proprietary, or that is the utility specific equations, if you like. So and also, if I could also add this, I know that all of you are on sort of mute and listening. Hopefully you have more questions, but AI ML is a knowledge companion that grows within an organization with time. It is not a calculator that we can go and buy in Office Works, where you can say, I'll give you the PHEC, tell me ORP. That's not the way it works. The way it is it has learned over the seasons to understand there is one set of unique combination of physical and chemical parameters for that water body, along with the weather conditions at that position, that result in most likely number of these bacterial content, this chemical oxygen demand, this biological oxygen demand. And that's the way it works. So it is not a calculator. So it is something that is evolving with the organization. Hence, my sort of push whenever I speak to sort of a very large gathering like this, I request people, in order to get there, we need to start the journey. That's where in a year's time, our AI ML capability in-house as an organization is unique, utility specific, very smart, and then we are learning. And at the same time, that has, coming back to Engineers Australia's recommendation, ability to share that knowledge of database across the utilities to understand the water digitization better.
We have a question in the chat here. What are some of the main predictive features that you've identified in the feature engineering step?
Yeah, well, that's in the feature engineering step, there are multiple. I'll give you an example. For example, PHEC, TSS, TDS, turbidity, ORP, and weather parameters like the humidity, solar irradiance, global horizontal irradiance, normal solar irradiance. The list goes on. But the feature engineering has to identify, if I rank all these 15 parameters that are contributing to these output that I require, what is the degree of relevance of every one of those? One is 35%, for example, pH 23%, EC 12%, and so on. It keeps going. Global horizontal irradiance 7%, normal irradiance 5%, and it all adds up to 100. And suddenly your humidity and everything falls off the end of the truck. You don't need them. That's what the feature engineering does in identifying those key parameters for predictive capability. So that's the process that we have to go through. And I hope that answers that, Vijay. So that you have identified in the feature engineering step, these are the things, and that's the method that we used to identify those parameters of significant importance. Thanks.
Any other questions at this time?
Yeah, feel free to if you don't want to type, you can ask me like what Blair is doing. Thanks. Okay.
Vishy, is there a need to change the lab testing frequency as part of this? I think I guess what I'm trying to get a sense of is what's the typical duration once you've provided that initial amount of data before you're finding people are getting a reasonable level of confidence with the data, where they're suggesting, yeah, this is pretty accurate at this point in time. Is that 1, 2, 10 cycles?
Yeah. Look, I don't know if any Southeast water colleagues are there or Hunter Valley colleagues are there. I don't know if they are there online, but as soon as they give the data, it will take 48 hours for the engines to become live. So you actually start to see, again, if you are giving me historical data, the system is predicting what is the most likely water quality at that given point. If you are giving me the sensory input, the system is giving what is the real-time online water quality at the moment. So we are able to do it. We have that opportunity. So when you give me the data in 48 hours, you are actually able to see the entire suite of them in front of you. These 14 parameters are coming online, and you're able to see and say, look, Vish, I would like to add arsenic to it, although there is no stress, but I have a nearby industry that is likely to be polluting the water, and then I want to check the arsenic content. You add arsenic to it as an add-on module. So you're able to do that. These are all minor additions, but coming back to the question, 48 hours, the system is live, and you can check that and say after initially once every week or fortnight, you can ask your lab people to say, look, can you please tell this guy he's 15% out on this, and the other. And then in the following fortnight, you are close to it by plus or minus 10%. It has already learned it. And that is utility specific.
Thank you.
Yeah.
Okay, doesn't look that we have any further questions, so we might begin to draw to a close. So firstly, I'd like to very much thank you, Dr. Karri, for sharing today. And obviously thanks for those that have attended and have joined into the conversation. Once again, this will be on our Knowledge Hub. So if you would like to a recap of the session, if you'd like to share this with your colleagues, there'll be the opportunity to do so. There is an offer here in terms of a potential trial. And so if there is interest in exploring a trial, really, which the extent in the first instance would simply be to provide some historic lab data. That's all that's required to basically get a view of the water quality within your system. Then you can reach out to us at the IWN, and very shortly we'll send out some communications on how you can contact us if you're interested. If you'd like more information, then there'll also be an opportunity for that as well. So we'll provide you with some contact details after today's session.
Yep. Excellent. I really thank you. Just before, I know everybody's patiently heard me. I know I can see the number is slowly going down, like we had 45 or something, or slowly now it's 27 as it's getting close to 12. Thank you all. And if you have any questions or anything that related to the water science or anything that sort of sensory inputs, the IoT, the AI, ML, is there anything bugging? Feel free to send me a note and I'll be very happy to answer your questions. And thank you again for this wonderful, it would have been so much different. Imagine with all these 35 people in a room, it would have been so much buzzing. And hopefully Melbourne Water would have organized a cup of coffee as well. So.
Very good. Well, look, thank you all. That concludes today's webinar. Once again, we'll send out some information post today's session, but I'd like to thank you for coming and have a wonderful day.